We all live surrounded by sound constantly. I mean, think about it. You've got the faintest rustle of leaves, maybe.
Yeah.
Or the hum of your fridge.
Yeah, the everyday stuff.
Totally. And then the ding of a notification on your phone, right? Compared to, say, a thunderclap or a jet engine roaring overhead.
Big difference. Some sounds are just there, background. Others really grab your attention, maybe even hurt.
Exactly.
Yeah.
So what is it fundamentally that makes that difference?
Yeah.
Why does one sound feel like, I don't know, a tickle, and another feels like a physical force?
That's really the core question, isn't it? And it leads us straight to a key property of sound waves. How much, energy they're carrying and delivering.
Ah, energy.
Yeah, it's not just if a sound exists, but it's strength.
Okay. So that strength, that power packed inside the sound wave itself, that's what we're diving deep into today, sound intensity.
Right, and our mission here isn't just to give you a definition. We want to unpack what sound intensity actually is physically, how we measure this, frankly, enormous range of sound strengths.
Enormous is right.
And how that physical thing connects to what we experience as loudness, sort of pulling back the curtain on the energy of sound all around you.
And this isn't just, physics theory floating in space. Understanding sound intensity, it's vital. For you science students, especially physics, it connects waves to energy transfer. Super fundamental.
And for biology students, it really shows off the incredible design of the human ear, how it interacts with the physical world. It's amazing engineering.
Plus, it pops up in technology too, right? From concert hall acoustics to medical tech.
Absolutely. So yeah, let's get into it. Let's unpack the power of sound.
All right. Where do we start? What is sound intensity?
Okay, so at its most basic, the source describes it as the level at which sound energy exists at a specific spot.
The level of energy, like how much sound energy is concentrated right here.
Kind of, yeah. But it's more specific than just presence. It's about the rate at which that energy is moving.
The rate. Okay.
The precise physics definition is sound intensity is the rate at which sound energy passes normally across a unit area at that location.
Okay, hold on. Rate, normally, unit area. Let's break that down. Rate at which energy passes. Energy per time. That's power, right?
Exactly. You got it.
Yeah.
And that's how we measure it. The standard unit is watts per square meter. Watts per square meter.
Watts per square meter.
Yeah.
And a watt is joules per second. So Will.mi is literally joules of sound energy flowing through 1 square meter every single second.
That's a perfect way to picture it. Imagine holding up like a 1 meter square window frame in the path of a sound wave.
Okay.
The intensity tells you how many joules pass through that frame each second. And the normally part, that just means we're counting the energy hitting it head on, perpendicular to the surface, the energy really going through.
So high intensity means loads of energy blasting through that square meter every second. Low intensity, just a trickle.
Precisely.
And intuitively, more energy hitting us should mean a louder sound. Yeah.
Absolutely. That physical intensity of the wave, that's what our brain processes and interprets as loudness. More intense physically means louder perceptually. Physics meets biology.
And this is where it gets kind of wild. The range of intensities our ears can handle is, it's staggering.
It really is. One of the most incredible dynamic ranges in any sensory system, honestly. The source material makes a point of this. At the super quiet end, the absolute softest sound a healthy ear can usually pick up, that's the threshold of hearing.
Okay, the baseline.
And the intensity there is minuscule, tiny. It's 10 watts per square meter.
10 to the minus 12. 1 trillionth of a watt per square meter. Wow, that makes you appreciate just how sensitive those little bits inside our ears are. Picking up on that.
It's pretty amazing. Now swing all the way to the other end. Sounds so strong they actually cause pain.
Yeah, definitely felt that sometimes.
That's the threshold of pain.
Yeah.
And the intensity there, according to our source, it's 1 watt per square meter.
Okay, wait. Let's compare those. 10 William for the quietest thing we hear, and 1 William for pain. 1 trillionth versus 1. That's 1 followed by 12 zeros difference. A factor of a trillion, is that right? 12 orders of magnitude.
12 orders of magnitude. A million times difference in energy flow. Think about that. It's like your senses being able to register both a single feather landing softly and, I don't know, a freight train hitting a wall.
And our ears somehow manage that incredible physical range and turn it into something our brain can actually make sense of.
Exactly. Which brings us to the next challenge, right? How do you actually work with numbers like 10 and 1? Calculating with trillions isn't exactly practical for everyday use.
No kidding. You'd need scientific notation for everything. We need a better way to talk about these levels.
And we have one, thankfully. The key is understanding how we perceive loudness. Our hearing response isn't linear. Doubling the physical intensity doesn't make it sound exactly twice as loud to us.
Ah, right. It's not a simple one-to-one thing.
No, our hearing response is fundamentally logarithmic.
Logarithmic. Okay, I remember logs from math. So it compresses the scale. Like big physical changes make smaller perceived changes, especially at the high end.
That's the core idea. Our biology uses a logarithmic mapping to handle that huge physical range. And that's precisely why we use the decibel scale for measuring sound intensity level.
The decibel scale.
Right.
Right, measured in decibels, dB. So this scale mirrors our hearing better because our hearing is logarithmic.
That's the beauty of it. And there's a formula that connects the physical intensity, I, to the intensity level, beta, in decibels. It's beta equals 10 times the base 10 logarithm of the ratio of I over a reference intensity I.
Okay, say that again slowly. It's 10 log.
10 log hour chat.
10 log hours. And that I, the reference intensity, that must be crucial. It sets the 0 point, right?
Absolutely critical. And it's defined very conveniently as that threshold of hearing we talked about.
The 10-year range.
That exact number. 10-year number. By setting I to the quietest sound we can normally hear, the whole scale gets anchored to our own biological hearing limits.
Okay, that makes sense. Let's test that formula. Let's calculate the decibel levels for those two thresholds, hearing and pain. Using IRO, that should really show how it works.
Good idea. Let's start with the threshold of hearing. Here, the actual intensity I is equal to the reference intensity IR. They're both 10 all way.
Right. So I equals IO.
Plug that into the formula. IO wa euro.
IO. Okay, I divided by I, that's just 1.
Yep. So I equals 1.
And the logarithm of 1, any base, is always 0 because, like, 10 to the power of 0 is 1.
Exactly. So IRO equals 100, which is 0 dB.
So 0 decibels. That's the threshold of hearing. But importantly, it doesn't mean 0 sound energy.
Right. It means sound energy at the reference level, the minimum level for human perception. There can totally be sounds below 0 dB. We just generally can't hear them.
0 dB is our starting line. Makes sense.
Yeah.
Now the other end, threshold of pain, intensity I equals a 1 well.
Okay. Plug that into the formula. Quan will and wangs, 10 will, 10 will.
The units Wilhelms cancel out. So it's 1 divided by 10 Wilhelms, which is 10 Wilhelm, 1 trillion.
So otters like 10 logaros?
And log base 10 of 10 outer is just 12.
Spot on. So otterbo is 1012 equal 120 dB.
120 decibels. Wow.
Oh, and there you have it. The entire audible range of physical intensity, that mind-boggling 12 orders of magnitude, from 10 wall to 1 Wilhelm EP, gets compressed neatly into a scale from 0 dB to 120 dB.
That really shows the power of using a logarithmic scale. It maps that huge physical reality onto our perception in a, well, manageable way.
It's a brilliant solution, really.
Okay, now, to really get a feel for how this log scale behaves, let's dig into that work example from the source, the one with the drills, because I think this tackles a common misconception.
It's a great one for that. So imagine you've got an electric drill going, you're standing nearby, and the sound intensity level is 80 dB.
80 dB. Okay, pretty loud. Need earplugs for that for too long.
Definitely. Now, here's the question. What happens if you have 4 identical drills all running at the same time, basically in the same spot? What's the new sound intensity level?
Okay, my first gut reaction, my linear brain, wants to say 4 times the drills, maybe 4 times the decibels. So 80 times 4, 320 dBs. But hang on, we just said 120 dB is pain. That can't be right. Logarithms.
Exactly. That's the trap. You don't add decibels like that. What adds up is the energy, the physical intensity.
Ah, right. So if one drill produces intensity I,
then 4 identical drills will produce a total intensity of 4I at that same point. The actual energy flow quadruples.
Okay, physical intensity quadruples. Got it.
Yeah.
So how does that translate to the decibel scale? We use the formula again.
We do. We need to find the new level. The original level was 10 logger II, and we know that's 80 dB.
Right.
The new intensity is 4I. So the new level, let's call it EV, is 10 logger I, 4II. Okay, 50, 10 logger or I. How do we compare that to the 80 dB?
We use a property of logarithms. Remember log A plus log A?
Exactly.
So we can rewrite log euro as log I for II.
Yeah.
Using that property, it becomes log arrow plus log arrow. Ah, okay,
Yeah.
I see. So the formula for the new level is 10 log euro plus log euro.
Multiply the 10 through.
The arrow plus 10 log euro. Hey, wait, that second part, 10 log euro, that's just the original level, though. That's the 80 dB.
Exactly. So the new level D is just the original level, 80 dB, plus this extra bit, 10 log euro. That term represents the increase in decibels due to quadrupling the intensity.
Okay, so the increase just depends on the multiplication factor, the 4. And what is 10 log euro? Source says it's about 10 times 0.602.
Yeah, roughly. So 7.602 is 6.02 dB.
6 decibels, just 6. So quadrupling the number of drills only adds about 6 dB to the sound level.
That's right. The new intensity level is the original 80 dB plus that 6.02 dB increase, which gives us 86.02 dB.
86.02 dB. Wow. Going from 80 to 86 doesn't sound like much on paper if you're thinking linearly, but it represents quadruple the physical sound energy hitting your ears.
Exactly. And it highlights a key rule of thumb with decibels. Doubling the intensity adds about 3 dB, because 10 log 2 is about 3. Quadrupling adds about 6 dB, as we just saw.
Yeah.
And increasing the intensity by 10 times adds exactly 10 dB, because 10 log EB is 10.
So a 10 dB jump means 10 times the energy. A 20 dB jump is 100 times the energy. A 30 dB jump is 1,000 times the energy.
You've got it. It really drives home how that logarithmic scale works and why adding sound sources doesn't just pile up the dB level in a simple way.
That example is super helpful. It really clarifies things. So intensity is energy flow per area. WMD dB are the practical logarithmic level. 0, 120 dB for us. But there's more to sound than just loudness, right? What about the pitch? The frequency?
Absolutely critical point. Our experience isn't just intensity, and this is where the source brings in another layer under hearing limits. It points out that our ear's response, specifically its sensitivity to that intensity, it depends on both the intensity and the frequency of the sound.
Meaning, a sound at one frequency might seem louder than a sound at a different frequency, even if they have the exact same physical intensity.
Precisely. Our ears aren't equally sensitive across the whole frequency spectrum.
So we have, like, favorite frequencies.
Yeah.
Ones we hear more easily.
You could definitely say that. First off, the range of frequencies we can hear is usually stated as about 20 hertz, like a really deep rumble.
Lowest note on a big pipe organ, maybe?
Yeah, something like that. All the way up to 20,000 hertz or 20 kilohertz. Kilohertz, that's a very high-pitched sound, like a dog whistle almost.
Okay, 20 to 20,000 hertz. That's the audible frequency range.
Right.
But our sensitivity isn't flat across that.
Not at all. The source highlights where we're most sensitive. It's in the middle range, roughly between 1,000 hertz and 4,000 hertz, so 1 kilohertz to 4 kilohertz.
1 to 4 kilohertz. Where are those pitches found, typically?
Well, crucially, a lot of the important frequencies for understanding human speech, especially consonant sounds that give clarity, fall right in that range. Biologically, it makes sense we'd be tuned in there. Okay, so in that sweet spot, 1 to 4 kilohertz, we don't need much intensity to hear things.
Exactly. Our ears are super efficient there. The source notes that an intensity level as low as 20 dB is enough to hear sound conveniently in that frequency band.
20 dB. Remember, 0 dB is the absolute threshold, so 20 dB is still really, really quiet. It takes almost no energy for us to perceive sounds at those pitches.
It's remarkable sensitivity. Now contrast that with the edges of our hearing range. Down at the very low end, say 20 hertz.
That deep rumble again.
Yeah. Our sensitivity is much lower there. You need a significantly higher intensity level for that sound to even register properly. The source suggests you might need around 35 dB to hear a 20 hertz tone comfortably.
35 dB compared to 20 dBs in the mid-range. That's a 15 dB difference. How much more intensity is that? 10 dB is 10 times 15 dB is ugh.
Well, 10 log euro x equals 1.5. X is 10 to the power of 1.5, which is about 31.6. So roughly 30 times more physical intensity needed at 20 hertz compared to 1 kilohertz just to sound similarly audible. Wow, 30 times the energy for that low bass. Okay, what about the high end? Near 20,000 hertz.
Similar story. Sensitivity drops off again. For a 20 kilohertz tone, the source indicates you might need an intensity level of around 40 dB to perceive it.
40 dB. That's 20 dBs higher than the 20 dB needed in our peak sensitivity range, 1 to 4 kilohertz.
Yeah.
A 20 dB difference. That's a factor of 100 in intensity, since 10 log ever is 20.
Exactly. So that really high-pitched whine needs 100 times the physical energy compared to a mid-range tone, just for us to hear it at a similar perceived loudness.
This explains so much, like why you might not hear a very low hum or a very high squeak unless it's actually quite powerful, while you can easily hear conversation.
Precisely. It's why things like equal loudness curves exist in acoustics charts showing the dB level needed at each frequency to sound equally loud. While we don't need to get into the specific chart mentioned, figure 7.2, the examples given 20 dB at 1 to 4 kilohertz, 35 dBs at 20 hertz, 40 dB at 20 kilohertz, they perfectly illustrate this fundamental point. Loudness isn't just about intensity, it's intensity plus frequency, interacting with our ear's specific response curve.
That's a really crucial piece of the puzzle. Biology shaping our perception of the physics. Now, you mentioned the hearing range stocks around 20,000 hertz. The source talks about sounds above that, right? Ultrasonics?
Yes, sounds with frequencies higher than 20 kilohertz are called ultrasonics or ultrasound. We can't hear them, they're too high-pitched for our biological mechanism, but they are still sound waves. They still carry energy.
And that energy can be used.
Absolutely. And this is where it gets really interesting for both science and biology students. The source mentions several medical applications of ultrasound that rely directly on the physics of sound waves, their ability to travel through tissues, and, importantly, transfer energy.
Okay, like what kind of applications?
Well, for diagnostics, it mentions using the Doppler effect with ultrasound. You send ultrasonic waves into the body, they bounce off moving things like red blood cells, and the frequency of the returning echo changes based on the speed of the blood flow.
Ah, so you can measure blood velocity without cutting someone open. That's wave physics in action.
Exactly. And of course, standard medical imaging, like seeing a fetus in the womb, that uses ultrasound echoes bouncing off different tissues to build up a picture.
Right, sonograms.
But it also mentions therapeutic uses, which really emphasize the energy transfer aspect. Things like using focused, high-intensity ultrasound to destroy tissue, like removing brain tumors non-invasively, or using the energy for therapeutic effects, like treating lower back pain, possibly through localized heating or other mechanical effects of the sound waves.
That's incredible. So the same fundamental thing, sound waves carrying energy can be used for hearing, for imaging inside the body, and even for treatment, just by changing the frequency and intensity.
It really shows how fundamental these principles are. It connects wave physics directly to biological systems and leads to powerful medical tools. It's a perfect illustration of how interconnected these fields are.
Definitely. Okay, this has been a fantastic deep dive. Let's try and summarize the key takeaways, connect the dots for everyone listening.
Sounds good. So we established sound intensity is fundamentally about energy flow. The rate energy passes through an area, measured in watts per square meter.
Right, and we saw the human ear handles an absolutely enormous range of these intensities, from a tiny 10 millimetro up to 1 millimetro where it starts to hurt. That's 12 orders of magnitude.
Which led us to the why of the decibel scale. Because our hearing response is logarithmic, not linear. The formula, 10 log I chop, uses the threshold of hearing Olametto as its 0 dB anchor point.
And that compresses the vast physical range into a more practical scale for us, roughly 0 dB up to 120 dBs for the threshold of pain.
And the drill example was key. It showed that adding sources adds their intensities, not their decibel levels directly. Quadrupling the intensity only added about 6 dB, highlighting that logarithmic nature. Remember, plus 3 dB is double intensity, plus 10 dBb is 10 times intensity.
Then we added the crucial nuance. Frequency matters too. Our ears aren't equally sensitive everywhere. We're most sensitive in the mid-range, around 1 to 4 kilohertz, where only about 20 dBb is needed.
But we need much higher intensities to hear the very low frequencies, like 35 dBs around 20 hertz, or the very high frequencies, like 40 dBs around 20 kilohertz. Our perception depends on both intensity and frequency.
And finally, we touched on ultrasound frequencies above our hearing, showing how the energy transfer aspect of sound waves is used in medical diagnostics and treatments, linking physics to biology and tech.
Yeah, for anyone studying science, physics, biology, this whole topic really ties together core concepts. Waves, energy, logarithm scales, biological adaptation, and technological application. It shows how beautifully these ideas interconnect.
It really does build a solid foundation for understanding sound all around us, from the quietest room to the loudest concert and even beyond what we can hear.
So here's something to think about as you go about your day. We talked about 120 dB being the threshold of pain, causing immediate risk. But health guidelines warn about prolonged exposure to much lower levels, say 85 dBb or even less, causing hearing damage over time. Given what we discussed about intensity being energy transfer, why is that? How does sustained lower-level energy actually damage those delicate parts of the ear?
Ooh, good question. And thinking about frequency sensitivity, what about animals? Many hear frequencies way outside our range. Why might that be useful for them? Do you think their sensitivity curves, their thresholds of hearing and pain, might be shaped differently based on their environment and needs?
Or flip it around to technology. Think about noise-canceling headphones. They don't just block sound physically, they actively cancel incoming sound waves to reduce the perceived intensity. How could they use wave properties, like superposition maybe, to effectively subtract sound energy reaching your ear?
Fascinating stuff to ponder. These are just some threads you can pull on as you keep exploring the amazing world of sound waves and intensity.